Hello students, we're going to move on and learn some more derivatives today. We're going to learn about how to find the derivatives of trig functions, and it's notes number 24. And we're going to approach this from a couple of different directions, starting with looking at the graphs of a couple of trig functions and then looking at the graphs of their derivatives and trying to kind of maybe guess what the derivatives should be. And then we're going to do the algebraic proofs. So the first thing I want to do is use my calculator to graph y equals sine of x and graph its derivative. So here we go. I've already typed it in. Make sure your calculator is in radians, so go to mode and then check to see that it's radians, not degrees. And then for the derivative, once you're in here, you can go to math and then in deriv, and then you type in x for the variable, and y1 is your function, or you can just put sine of x in the parentheses there, and then you put x for the value. And for a window, I'm going to go to zoom and choose zoom trig, which is number 7. So the blue one is the sine graph. Hopefully that looks familiar. And the red one is the derivative of it. So I'm wondering if that red graph looks familiar to you. Notice that it's also oscillating just like the sine graph is, except that it's offset and it goes through 0, 1, and then this right here would be pi over 2, comma 0, and this would be pi, comma negative 1, etc. So this red graph, that actually looks like the cosine graph. So the guess at this point would be that the derivative of sine x is cosine x. And now I want to do the same kind of thing, but this time I'm going to look at the graph of the cosine function and its derivative. So the blue one is the cosine function. Ooh, that does look like the derivative graph we were just looking at a moment ago. And then the red one is its derivative. So does the red one look familiar? The red one looks like we took the sine graph and flipped it upside down, which would mean that we took the opposite of the sine graph. So our guess would be that the derivative of cosine of x is the opposite of sine x. Now we're going to prove that algebraically, which is what's next. All right, so I already have the steps written down. And in order to do this proof, by the way, you do not need to write this proof in your notes. I don't want you to spend the time on that. In fact, if you want to speed up the video and watch it at 1.5 times or 2 times the speed, that's fine. I just want you to see and experience the proof, but you don't have to be able to recreate it. So these proofs both rely on some of those limits that we learned in the last chapter. In particular, we focused on this one. The limit of sine of x over x as x goes to 0 is 1. And then the second one was also mentioned, but we really didn't spend much time with it at all. Okay, so if you want to find an algebraic proof for the derivative of sine x, you go back to your definition of derivative. And the definition of derivative I'm choosing to use for this problem is the limit as h approaches 0, 1. So we plug in our function there. Now, in this proof, we use a trigonometric identity that perhaps last year you guys actually didn't get a chance to see because due to the pandemic and the very abbreviated learning we did at the end of pre-calc, you might not have seen all of the trig identities that you were typically supposed to see. So here we go. The sine of x plus h can be rewritten as sine of x cosine of h plus cosine of x sine of h. We call that a sum identity for sine. Sorry if you didn't get to learn that last year. You'll just have to take my word for it. So now what I'm going to do is a little bit of rearranging. I took the first and the third terms and put them together and factored the sine of x out of them. And then this here is just the middle term. I wrote it a little bit differently. You can think of cosine is just cosine over 1. Sine is sine over 1. It doesn't matter. Okay, so now that we have that, we can find the limits. So the limit as h goes to 0 of sine x is just sine x. There's no place to put the h or the 0. And then the limit of cosine h minus h over h as h goes to 0, that's this special one over here. So that is 0. And then this one here is just cosine x because just like the first one, there's no place to put the h equals 0. And then this last one here, the limit of sine of h over h as h goes to 0, that is 1. That's that other special trig limit. So once we simplify that, all we have left is cosine x. So yes, just like we thought from looking at the graph, the derivative of sine of x with respect to x is cosine x. And I'm going to have a slide in a minute that has all of these written out, so you can just wait until we get to that point. Same idea for the derivative of cosine. So what we want to do is write it out using the definition of derivative, and then there's an identity to break up cosine of x plus h. Once again, you probably didn't learn that identity last year. I wish you had. I'm kind of sad about that. But it's equivalent to cosine x, cosine h minus sine x, sine h. And now, just like we saw in the last proof, we can rearrange. So I took the first and third terms and factored the cosine of x out of them. And then this one right here is just that middle one. And then we can evaluate each of those limits. And we end up with cosine of x times 0 minus sine of x times 1. So when you simplify that, you get negative sine of x. So just like we saw with the graph, it is true that the derivative of cosine x with respect to x is negative sine x. So I would memorize all of these. I mean, I guess this year memorizing isn't as important because you're using your notes, but I mean, it helps you to be able to work the problems more efficiently if you memorize some of the basic ideas and you don't always have to look them up. Okay, now we have 4 more derivatives to figure out, and I'm going to just prove these based on the other 2. So we know that tangent of x is equivalent to sine of x over cosine of x. That's one of our identities that we did learn. And that is a quotient. So I'm going to find the derivative using the quotient rule. So we have the bottom times the derivative of the top, and the derivative of the top would be the derivative of sine of x, which we just learned was cosine of x, minus the top times the derivative of the bottom, so minus the top sine of x times the derivative of the bottom, and we just learned that the derivative of cosine of x is negative sine x, over the bottom squared would be over cosine of x squared, and we write that as cosine squared x. So what we have here is cosine squared x plus sine squared x over cosine squared x. Remember, you cannot cancel the cosine squared x's because of the plus. But hopefully you remember from your trig identities that cosine squared x plus sine squared x is 1. So this is 1 over cosine squared x. And hopefully you also remember that 1 over cosine x is the same as secant x. So this is secant squared x. So the derivative of tangent x with respect to x is secant squared x. We can do the similar kind of thing for the derivative of cotangent x because cotangent x is cosine x over sine x. So once again, we can use the quotient rule, and if you feel like it, you could pause the video and you could work it out yourself and see if it turns out to be the same as what I get. So we have the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And when we simplify that, we have the opposite of sine squared x minus cosine squared x over sine squared x. I'm going to factor a negative 1 out of the top. Negative 1 times sine squared x plus cosine squared x over sine squared x. And remember, once again, sine squared x plus cosine squared x is 1. So we have negative 1 times 1 over sine squared x. And 1 over sine x is the same as cosecant x, so this is negative cosecant squared x. So the derivative of cotangent x with respect to x is negative cosecant squared x. Okay, 2 more to go. So let's think about secant x as being the reciprocal of cosine. So it's the derivative of 1 over cosine x with respect to x, and we can use the quotient rule on this as well. The bottom times the derivative of the top. Keep in mind the derivative of 1 is 0, minus the top times the derivative of the bottom over the bottom squared. So this gives us sine of x over cosine squared x, and we can break that down into sine of x over cosine of x times 1 over cosine of x, and the reason we would want to do that is because then we can change sine of x over cosine of x to tangent x and 1 over cosine x to secant x. Now the way we usually write this is the derivative of secant x is secant x tangent x. So we usually just put the secant first. Not that you would have to, but that's just the conventional way to do it. And finally, for the derivative of cosecant, we know that cosecant x is 1 over sine x. So we have, using the quotient rule, the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And that works out to be negative cosine x over sine squared x. And let's break that up into negative cosine x over sine x times 1 over sine x, so that we can use our identities to write that as negative cotangent x times cosecant x. So the derivative of cosecant x with respect to x is, here's how we write it, negative cosecant x cotangent x. Okay, so now we have proofs of all of them, and here they are all together. So you can make some observations which help you to memorize them. One of the observations is that everything that starts with a C, cosine, cotangent, cosecant, those are the ones that have negative signs, and the only ones that have negative signs. Also, you might notice that tangent and secant seem to like to play together. They're good friends, whereas cotangent and cosecant like to play together. They're good friends. Okay, so you'll want to work on memorizing those. And what we're going to do to end the lesson is do some examples where we incorporate these in with the other rules we've had. So, number 1 is y equals cosine x minus 2 sine of x, and we're going to find the derivative. So if you want to call it dy dx, that's cool. If you want to call it y prime, that's cool. So what we're going to do is take the derivative of each term. The derivative of cosine of x is negative sine of x, and then minus, and then the derivative of 2 sine of x, well, we just have to leave the 2 and multiply by the derivative of sine of x, and the derivative of sine x is cosine x. So once you get that answer, you can look it over and determine if there's something you want to do to simplify it. But for this particular one, it doesn't look like there's really anything we need to do, so I'm going to leave it like that. Number 2 is a product. Y equals e to the x times cosine x, so we're going to use the product rule. This time I'll call my derivative y prime. So we have the first times the derivative of the second plus the second times the derivative of the first. Now, what would I do to simplify that? Well, you have some options. If you want to, you can factor e to the x out of both terms. And then when I write the rest, I'm just going to rearrange the order. So cosine x minus sine x all times e to the x, that's one way. Or if you don't want to do that, if you don't want to factor out the e to the x, you don't have to. you could write just e to the x cosine x minus e to the x sine x. That would be another good way to write your answer. Either one is good. Okay, number 3 is a quotient. And so we're going to use the quotient rule, and notice that inside the quotient we have a sum. So that's going to make it a little more tricky. So we just have to be really careful and take our time. So we have the bottom times the derivative of the top, and the derivative of x is 1, minus the top times the derivative of the bottom. Now the derivative of a sum is the sum of the derivatives. So first the derivative of tangent x and then the derivative of secant x. And the derivative of tangent x is secant squared x. And the derivative of secant x is secant x tan x. And that's all over the denominator squared. So that's all over tangent x plus secant x squared. And please note that that's not the same thing as tangent squared x plus secant squared x. Remember, if you're squaring a sum, you have to FOIL. So whether or not we end up foiling that, we'll see. Let's wait and see what happens with the numerator. So what I want to do is some distributing and see if anything special happens. So we have, actually I want to stop and look at it and realize that we have tangent x plus secant x there. We have tangent x plus secant x there. And if we were to factor secant x out of both of those terms, we would have tangent x plus secant x there as well. So we would have that as a factor of all of the terms. So that's what I'm going to do next. Leave the first part alone. Factor secant x out of the second part. And if you want to write that as tangent x plus secant x, you can. Now, if you factor tangent x plus secant x out of both parts of the top, it looks like this. Tangent x plus secant x times 1 minus x secant x. And that's over tangent x plus secant x squared. Cancel one of those. And what we have left will be our answer. Okay, I think that's all. Oh, one more. Goody. Okay. A mass on a spring vibrates. Its position at time t is x of t equals 2 cosine t over e to the t. Sometimes position is given as s instead of x, or it could be h for height. It really doesn't matter. And in this case, our variable is t instead of x, and again, that really doesn't matter. So find the velocity and acceleration. So the velocity is the derivative of the position. And the acceleration is the derivative of velocity. So basically we have to find the derivative, the first derivative and the second derivative. So for the first derivative, I'm going to call that velocity. We have to use the quotient rule. So we have the bottom times the derivative of the top, and that would be negative 2 sine of x, or sine of t, minus the top times the derivative of the bottom over the bottom squared. Now you can write e to the t squared, and then you can use your exponent rules and multiply the exponents, and it's the same thing as e to the 2t, or you could write it as e to the t times e to the t. And the reason I want to do that is because we're going to be able to cancel the factor of e to the t, just like we did in number 3 when we factored out the tangent x plus secant x from both parts of the numerator and then canceled it. Let's go ahead and do that here as well. So just to save time, I'm not going to show my factoring out the e to the t, but because it's in each term, we can go ahead and cancel it. Only because it was in each term. If it was only in one part of the top and not in the other part of the top, you couldn't do that. So now what do we have? I'm going to factor out the -2. So we have -2 times the quantity sine t plus cosine t over e to the t. That's velocity. It's slightly more complicated than position was, and we have to find the acceleration, so we're going to take the derivative one more time. So the acceleration is the derivative of velocity, so we're going to go through and do the exact same thing again using the quotient rule. The bottom times the derivative of the top. So -2 times the derivative of sine is cosine, the derivative of cosine is negative sine, minus the top times the derivative of the bottom over the bottom squared, and once again we can just think of that as e to the t times e to the t. And just like we did before, we have a factor of e to the t in both terms of the top that we can cancel with the bottom. And now let's see what we can do. So if I distribute, actually if I factor out the -2 from both parts, I have then cosine t minus sine t minus sine t minus cosine t. That came from this minus being distributed. The other -2 was already factored out, all over e to the t, and you can cancel your cosine t and your minus cosine t. You can add those sine t's together, so you have -2 sine t, multiply that by the -2, and you have 4 sine t over e to the t, and that's the acceleration. So all three of these functions, position, velocity, and acceleration, are similar, I would say. They all end up with the same denominator and slightly varied numerators. Okie dokie, here's your assignment. Thank you. Let me know if you have questions, and have a good day.